I wanted to take a couple of minutes of time talking about linear programming and the underlying issues, ideas, concepts behind Solver. And the best way to do that is QM for Windows. You can see the platform right here. And I'm just going to go to linear programming. Of course, we did a maximization problem. However, this transportation problem that we're working with in the textbook is different. It actually minimizes for cost rather than maximizing for profit. The tables and chairs example that we had was maximizing for profit. Here we're going to minimize for cost. And I'm looking at a problem regarding turkey feed. Again, rather than maximizing for profit, we're minimizing for cost. We've got three constraints, two variables. Our two variables are going to be brand X and brand Y of a certain turkey feed. And the constraints are going to be the nutrients that are required for the turkeys. So I'll click OK, go into that, brand X and brand Y. And I'll go through this rather quickly, but I'm sure you'll get the gist of it. And the turkey feed, let's call it zinc. The second nutrient, vitamin A. And the last one, let's call protein. Oh well. And so every ounce of turkey feed costs 2 cents for brand X. Again, we're in brand X. For brand Y, let me put that in as a capital. For brand Y, let's say it's 3 cents. Now with zinc, there are 5 units of zinc in every bag of brand X or every ounce of brand X, and there are 10 units in every ounce of brand Y, and the total daily requirements have to be 90 or more, so greater than 90. For vitamin A, there's 4 units in brand X, and in brand Y there are 3 units, and that's got to be greater than 48 units for the daily recommended amount for these turkeys. And then the amount of protein is 0.05, actually 0.5. In brand X, every bag or every ounce of brand X, and in brand Y, it's 0. And it's got to be greater than 1.5. Notice the proportions in here, 5, 10 to 90. They've got to be reasonable. 43 to 48, and the protein 0.5 and 0 to 1.5. Again, we're minimizing for costs, and we're going to run this linear program in a second, but the key is rather than maximizing for profit, we're minimizing for costs, and we solve it. And we can see the answer. We need 8.4 ounces of brand X, 4.8 ounces of brand Y, for a total cost of 31.2 cents per turkey. And of course, we don't have the integer requirement in here, but no biggie. Put up the graph, and with the graph, let me bring this down a bit. With the graph, you can see the feasible region is on the opposite side. When we're maximizing for profit, we wanted to maximize, get the most money we could. Here we're trying to decrease costs to the lowest possible level. So anything out here is going to fulfill the turkey's daily calorie, zinc, vitamin A, and protein requirements, but we want to do it at the lowest possible cost. And so we look at the feasible region that, the lowest feasible region really is the corner points. We could have this much of brand Y. What's that? About 14 units of brand Y and 18 units of brand X. But the lowest possible cost is 8.4 ounces of um, brand X and 4.8 ounces of brand Y. And that would give us all the daily requirements for our turkeys at the lowest possible cost. By the way, here are other areas within actually the corner points. This is the lowest cost corner point right here in the middle. So it gives us our different options. In addition, this is, as we had used earlier, the uh, QM for Windows that allows us to use many of these quantitative methods. And we'll probably see a little bit more of this later on. It can be easily downloaded for free off the internet at Pearson, I believe. Matter of fact, if you Google Pearson publishers and QM for Windows, you could probably pick this up real quick and easy. Thank you very much.